Hello, hello, hello. On stream, on here on locations, we have still some seats available. So for the people in the back, the front rows are available as usual. So welcome everybody to our .NET Community Austria March 2025 meetup. Thanks to all for joining here on location at Square in the new office or on stream on Twitch and YouTube. Um, Thanks for being here. Yeah, thanks to Square for hosting this event. Yeah, in the new office, quite an impressive view. Uh, Thanks for having us here. Also, quick thanks to our other sponsors, Rubicon and JetBrains. Rubicon is supporting us financially. JetBrains with a 12 months license that we raffle. How you take part in the raffle, the usual. Please join the chat. Also, the people here on location, quickly in the chat and enter hashtag JetBrains. And at the end of the after the talk, we will raffle it. Quick some community news. So there are quite some events in the next weeks. So on March 18th, we have the Azure Meetup Vienna Global AI Bootcamp. Here, March 21st is the next Coda Dojo in Vienna. On March 27th, our friends from the .NET Stammtisch Linz have Rainer Stropek with referees sing about C Sharp. Yeah, in Linz. April 4th is again the next Coda Dojo in Vienna, and April 9th is our friends in Graz have meetup about AI everywhere, local versus cloud, deployment of large language models. So quite some events in the next weeks. For us, we just got the next event planned for April, so April 29th. Um, Raul and David, sorry, we'll talk about the data sync community toolkit, effortlessly integrating data in modern offline client. Meetup event will go online in the next days. Yeah, and we are at Tech Talk again. As you see, the May slot is still open. So if you have an interesting topic that you want to share with the community, please reach out to us here on the event or via email, and we get something organized. And with that, I'm done. And now, Job, uh, our speaker of the day with building event-driven microservices at scale with Azure Cosmos DB. Thank you for being here. So, quick technical change.
So now we should connect to my laptop. And the HDMI cable is on the other side, so it's even like shorter.
Yeah.
I think I'm doing that, but let me just. You mean in a StreamYard? Yes. Okay. Now I have two screens and I don't know where I am, so that's even worse. So where can I check my screens? Okay, I think this is better. And StreamYard. Present, share screen, entire screen. And if I switch that.
And if you, when you hide the small,
Hide that. And is it fine on your side, Stefan? Okay.
Let's start the presentation. Let's see what's happening then. We have presenter mode.
Haha. I mean, it's fine, right? You need to just see the slides in my notes. Okay, so slideshow, yes, and since setup slideshow and monitors, primary slideshow. I mean, I just extended that. Let's just go to display settings. No. Display. No. Okay. Let me just again play it. Is it fine now? Okay. What do you see on stream? Just the slides? Okay. And if I switch, okay, that's that one. Okay, let's see. Maybe we don't have any coding session, but I can't see it. Okay. No, I'm not. I probably don't change anything. Okay, thanks everyone for participating. I hope we have a nice evening together, and like if this is disappointing, we have great pizza, so there is still hope for there. And today we want to talk about building event-driven systems at a scale with Azure Cosmos DB, which is actually a title to convince you guys to participate here. And it's just would be like my lesson learned for Azure Cosmos DB when I tried to make a system like this, right? So let me go with introduction. This is not working, so probably. Okay, I'm just going directly to the problem. So everything was fine when we were creating software. This is like all valid software architecture diagram for us. Like we have a client sending a request to some backend service, and then we have a database that stores or retrieves the data from there. And everything was really fine until we started to gather more customers because we want to sell more for our company. And then the API become like a bottleneck in our system. And we always had great solutions for them. And recently we just scale out everything, right? So we added more instances, and then we could handle more requests coming to our system. And this is fine until all those requests ended up to the database, and we need to handle the database need to handle all those requests anyway, right? And it became a bottleneck. So we thought maybe we go a little bit, do some offloading of the database. We changed to another pattern, which is, if I remember correctly, it is WebQ. I forgot the name of the actor over there. So it was like we have more requests, we queue the requests in somewhere in between, so we have a buffer, and then we have some other services picking up those messages from the queue and talks to the database. So now we bought ourselves like some time to process all those requests that are coming into our system, right? Yes, until the queue became the bottleneck, because then we had a lot of messages in our queue piled up together, and we had just one person answering to those queues, to those messages or events in the queue, right? And the solution was, again, scale out. So we added more of those people. So we could now process more messages from our queue, and we put them into the database. But again, we end up like having our database being the bottleneck. And yeah, these were like kind of the problems where whatever we were doing, in our architecture, at the end of the day, we were ending up our database becoming the bottleneck. I mean, yeah, maybe 2 million requests per second, 10 million requests per second, but we always want to grow more and more, right? And then we need to think about the actual problem, that we are shifting it from like one component of our architecture to another component. And so we gathered here at the square. We are humans, but in our hearts, we are engineers. And there are amazing colleagues of mine, like amazing people at the square, except one, if you could spot him. Yeah, no? If someone spot him, they will get discounts for the Code Crafts conference, no? This is the guy that is not awesome here, just the one. I'm Shahab. I'm a software developer for around 20 years. It just happened to be a software engineer. And currently at Square, I'm focused on software architecture and software transformation, helping our customers to modernize their systems. And I'm I was always .NET and C# enthusiast. I grew up with .NET. I started with .NET 1.1, .NET Framework, and C# 1. So I could actually say I grew up with C#, and that's why I'm really love this language, and nobody allows to criticize that. So, and I'm a father of 2 amazing child, so it is expected of me to say dad jokes. And when I'm saying that, I expect everyone just laugh because I don't want my feelings to be hurt. And I'm also doing some activities outside of the job. I'm writing blog posts. I'm creating contents on the video. Here's the QR code you could scan if you want to see those things. I'm also a Microsoft community leader in MS Farsi community and Microsoft Zero to Hero, which respectively we share knowledge in Persian language and English. So if you're a Persian speaking person, contact me. Also, like for English speaking people, contact me if you want to have a session in those communities. Super welcome. And I'm actually disappointed nobody take their phone to scan the QR code, which is, oh my God, you lost your chance. I'm sorry. No, I'm kidding. You could scan that. Yeah, okay. Back to our problem. We wanted to solve that, but because we were on an event-driven architecture, first we need to look into some of the patterns, some of the jargons that we could use, and then see how we could leverage Azure Cosmos DB and what does it have to that could offer us like to tackle this problem that we saw earlier. So in an event-driven architecture, we have 3 main components. We have a producer, we have something in between for buffering, whether it's event bus, message bus, whatever you name it, and then we have a consumer. And all of the software components are reacting to events. So everything is an event. We just inform other parts of our system something happened, and if they are interested, they could subscribe to that, they could react on that event and do whatever it is needed to do based on that scenario. And yeah, events are the means of communication. And one of the greatest benefits is that it promotes loose coupling. So these components of our architecture doesn't need to know about each other. There's just a contract in between, which is the event that we are designing, and that's it. And then they could design their own system, like however they want to react. And when we are talking about events, we need to be aware of different type of events. We have events that don't have any key. It's just like a matter of fact that has happened in the system. Like, I don't know, customer engaged with a book or something. You just track the behavior of the customer. You don't have anything there. And then you have entity events, which are kind of a snapshot of the state of the entity that you have. An entity is something that we could identify it by a unique identifier. So it has a unique identifier. Every event is just stating what is the state of this entity at that point in time. And then we have keyed events. For keyed events, we have a specific key designed for a series of events that could be partitioned together. They could be grouped together for various reasons. It could be like keeping them in locality. So whenever we want to do something, they are all together and we could access them as fast as possible, right? So this is the purpose of the keyed events. And this is something that we will do in our, we will see later how we could leverage that in our system. And it would be disappointing if we talk about event-driven systems and we don't talk about events and commands and their differences. So events are stating a fact, something that has happened. You cannot change it. It's immutable. And it could have 0 to many consumers, which means like 0 to many components in our software design to be interested in the thing that has happened. And it has only one sender. And the ownership of this event is the sender. The command on the other side, it has one component that subscribes to it, which is responsible for when some other components in our system sends a command, which means that we could have multiple senders, but we have only one consumer of this event. And it's responsible to handling this command. And the ownership of this contract, this command, is at the consumer side. So this is like the differences between them. And there are also related patterns when we are doing that. CQRS, command query responsibility segregation, and it separates the read and write models from each other. So I could design my system if my system is heavy read system, I could design it separately for that scenario. Or if I'm heavy write system, I could separately design my system for that scenario, right? So this is like the separation that it gives to us. But there are also like misconceptions in here that they always are related to event sourcing. Like whenever you hear event sourcing, people say you do CQRS, or whenever you hear CQRS, it is expected to do event sourcing, but it is not. They are like two different design patterns. You could just use them as necessary. And there are also like a myth that when you are doing CQRS, you need to be asynchronous. It is not. And actually, I think Jimmy Bogart has like an article that describes all the myths around CQRs and event sourcing, which is really a good article, highly recommended. I don't know if I have the link. I have it down there, but probably not really readable on this. But you could, I mean, you just Google it, Jimmy Bogart CQRS myth, and then the first link probably is what you need to go and read. So in our system, we kind of ended up with this architecture. And so we had the client sending the request to the API. The API just writes it to the Cosmos DB. We will see like how Cosmos DB scales and what are the things that we need to care about when we are designing our system over that, the limitations and everything. And then we had like an application, which here it is like an Azure function that forwards the request to somewhere else. In this scenario, it is an event hub on Azure, but it could be like a Kafka, right? Whatever, you need to forward this system there. And also we have another Azure function that listens to the stream of events that are written to this Cosmos DB and creates some projections or read models in our system. And yeah, at the end, we will see this architecture again. And other services could also listen to the event hub and see like whatever event is coming to the system, they are doing, sending an email or updating the inventory or something like that. So the reason for Cosmos DB is that it also horizontally scalable. So if the number of requests increases, we could increase the number of instances of our Azure Cosmos DB that processing those things easily. It's not that we couldn't do that with traditional databases. It was very hard to do that. But with Azure Cosmos DB, we could do that considering knowing some concepts and considering some limitations. And it's also a multi-model database, so you could use it for document databases, you could use it as a key value database, you could use it as a graph database, and it's also globally distributed. So if you have like different kind of customers, let's say United States, maybe these days Canada, and Europe and Australia, then you could have like 3 instances globally distributed and share the data between them, right? And when we talk about scalability, we need to consider 3 dimensions. The first one is functional decomposition. It means that we have like one database per applications that we are doing, which actually fits maybe very well with this microservices concept that we have, that each bounded context or each microservice has its own database, right? And they just separate the databases, so each of them have different load, and then you could just design this database based on that one. The other axis is replication. We know that from, I don't know, 20, 50 years ago, we always use replication, right? We had replicated we usually had like one write instance, and then we replicate the data into multiple instances and using them as read databases in traditional systems. And then we had like replicated the data. In some databases, you could even have multi-write replication and like bidirectional things, which is really hard, like, but possible. The other thing is sharding or data partitioning, which means like separate the data from each other and group the data in different instances. So you could have smaller instances of the database handling a smaller portion of the data, of the overall data. And then you should know where this data is stored and then just forward the request there. Let's see that. So here we want to talk about sharding. In sharding, we have a single logical database, and we have a cluster of those instances that together they are forming a logical instance. It's not, they are separate physical instances, but they are forming a logical instance of a database. And nodes have different data. So the first node has, I see blue in here. I don't know what color is there. Yeah, the blue data, and the other one has the green data and yellow or orange, whatever. So the data is separated into these different instances. And every time a request comes in, we could spin up another instance and just shift the part of the data to that instance, right? If there's more requests coming in now, we could just spin up another instance and put the, I don't know, the red data over that instance. And then it is just responsible for the red data. I actually have red data. I didn't. Okay, so the read request comes in. This logical database knows where the data is stored for this yellow request that this comes in, and just forwards the request to that instance. And if another request is joining, which now it is wrong because it's the, yeah. So we have a bug in our system, but you know the concept in here. So it just forwards data, and it knows where the data is, and that is based on that keyed events that we have defined. We have a key defined in our system, and this logical instance knows where the data is based on that key and just forwards it to the appropriate physical instance for handling that database. I see a deja vu. Yeah. This one is the correct one. So, okay. And there are advantages. Oops. So one of the advantage is that each server needs to deal with a subset of data. So if I have 1 trillion of data and I have, I don't know, 10 instances, my math is not good. I need to deal with, I don't know, 10 gigabyte of data, for example, right? Or 10 terabyte of data, whatever. It's smaller, so I could manage it easier. We have fault isolation. If one instance goes wrong, goes down, the rest of the system is still available. Only we need to make sure that this instance will be back again. We have reduced memory and I/O. We have cache utilization, so the data could be cached at each instance like separately based on how the usage pattern for those data is, and also improves transactional scalability. Previously, if we had like an order table inside our relational database, we had to log the whole table for everyone, kind of like if we want to go with consistency and those kind of stuff. But now, this order table is separated into multiple instances, so every instance has its own transactional scope. It's not in conflict with the other instances of the server running on. And of course, in everything with software engineering, there are also disadvantages. I was commented that I should remove the images, but because, yeah, I'm a Friends fan, and I don't know, it was, yeah. Sorry if it's just scared, yeah. Increased application complexity. Now I need to know where the data is stored. I need to store the related data on the exact instance of my server. So more complexity. And we need to design a partition scheme. The partition scheme is just another fancy name for that keyed entity that we talked about, right? It is just a mechanism that we group all of these related data with each other, and we put them on a server. Why we need to care about? Because if we design it wrong, then we need to redesign it, and that means we need to move all the data that are stored in server A to move to server B, and then server B to server C, and server C to server A. Like, so this is something we need to do. And sometimes we also need to repartition the data. Requirements of our system changes, and then the old partition key might not be valid anymore for our new requirements that are coming to the system. So we need to design a new partition scheme, and that means we need to shuffle the data again on the right server. And improper traffic distribution. This is very interesting. We have all those data stored on different physical instances. Let's consider we design a system for a concert, selling tickets, right? And I'm having a concert, and Taylor Swift at the same time has a concert, right? And then definitely there is a different traffic from the server that stores my tickets, concert tickets, and Taylor Swift's concert tickets, right? Definitely my fans do not have any problem buying tickets because it doesn't have that much traffic to be handled with that server. Oh, performance issues with queries. Yeah. So as far as we know this key that we could fetch all the related data with each other, we should be fine, more or less. We are fast because we know where to go and how to fetch the data. But if the query goes through who sold more tickets, right? It cannot find who we are talking. It needs to scan all the servers going through my tickets, going through Taylor Swift, I don't know, someone else, and grab all the information from those servers and then aggregate them, for example, together. This is called cross-partition query. So I need to go, it's like table scan in old systems, right? I need to see all the data and all the servers just to be able like to satisfy these queries. So this is something we need to care about. So a container, let's define some limitations in here that we have with Azure Cosmos DB. A container is a fundamental resource that stores our data and serves as the unit of scalability and performance. So everything that we want to think about the scalability and performance, we need to think about the container. But it also has some limitations. In a container, we store documents. One document cannot exceed 2 megabytes of data. This is important because when we are designing our events, when we are designing our data model, we need to make sure we are not exceeding this value. And why it is important? Because when we have document databases, we don't have this one-to-many, we have the one-to-many relationship. We are not storing them the way we used to store it in a relational database. So there are different ways. For example, I could embed all those one-to-many items inside one document and like have an array as a JSON and just store everything there. Or I could make them separate documents and like have references from here to the other one and go and fetch the data. So these are things that might happen that we exceed these 2 megabytes of data if we don't design well. And then we have logical partitions, which is the partition scheme that we have designed. In a logical partition, we could store up to 20 gigabytes of documents that we have in general. It could be one document, it could be millions of documents, but it cannot exceed 20 gigabytes of data. And then it is guaranteed by Azure Cosmos DB that all the documents having the same partition ID will be stored on the same physical instance. So all the blue documents will be on this physical instance and all the red and white ones will be on the other one. And as the system scales, it could spin up another physical instance and move like some of the data between those things. So moving, for example, the red documents to the next instance. But the physical instances cannot exceed more than 50 gigabyte of data. These are like the limitations. And so if I have a 100 gigabyte of data, then I should at least have 2 physical instances. So I should design my container. I could create my container in a way that it will spin up to different physical instances. And then we have the request units. The request units is like kind of a money. It maps memory usage, CPU usage, the amount of data we write or the amount of data we fetch from the database into this concept. And every container, yes, every physical partition could handle 10,000 request units per second. And a request unit for a document which is 1 kilobyte of data, and we know its partition key, and we know its ID or its unique identifier within this partition, will be 1 request unit to fetch that data. So 1 kilobyte of document, knowing its partition key and ID, and fetching it will be 1 request unit. And then we talked about transaction scope. So transaction scope in Azure Cosmos DB is not the physical partition, it's actually the logical partition, which gives us more flexibility. Again, considered like selling tickets for the concert, you could design your system in a way that every singer is like a partition ID, so we don't conflict with each other when we have like to make sure the transactionability of the system, right? But it might be a problem for someone like Taylor Swift, which has like a lot of requests coming in the system, and you want to still make sure that they are not in conflict with each other. So you could change the system to design, for example, you have the hall that the concert is going to happen. You could partition the hall into like east side, middle side, west side, middle west, and then partition that, like your partition key be this kind of group of seats, and then still you have transactionability now between those seats. So you could even like separate that more inside this transaction scope. So the transaction scope is do something. I think I'm clicking too much. So if those documents are not written, come on. So if these documents are written together and everything is fine, then we have the transaction successful. And if it is not, then obviously we expect that the system just removes the one that was already written because the whole transaction failed. And why this transaction thing matters in our system? Consider this. Is it visible? Is it readable? I mean, yeah. So this is like a traditional problem in distributed system. We have dual write problem. Where's the problem? The problem is here. Here we fetch the order, whatever it needs to do. At this line, we are writing it to our database. And at this line, we want to inform other systems about what has happened just in our system, right? And if here our system crashes, we just write something in our system, but we fail to inform others. So the others do not know if an order was made in our system or not. And one solution is like to switch these two lines. So first inform everyone about what has happened to our system, and then write it to our database. But still, if the server goes down in here, we informed everyone about what we are going to do, and we never do that. It's basically my life with my wife, because I'm always telling her that I will do something and I'm not. So yeah, I think she'll understand. The solution is like to wrap this event emitter, fake it, instead of actually publishing it to other systems, we store it in the same transaction as the actual entity that we are storing in our system. And then we have some other systems that understands these events and fetch them and on its own publishes that to the message broker or event bus or whatever we have. And this commit async is actually saving those two on the database. So this one is also like an in-memory representation, like an EF core. When we are saving, like adding to DB context, we are not really saving it to the database, right? Something like this. And yes, it is important also to know how Cosmos DB scales behind the scene. So if we have just one region, I will have one leader and I will have 3 follower instances. So these are like separate instances running inside one region. So by like built in, I will get a scalability kind of in here. So if requests are coming, or if the leader goes down, we could have like another follower taking the role of a leader, and then like we have high availability, right? And if we also want to distribute our systems globally like this, so having some instances in United States and having some instances in Europe, it even gets more complex. So now one of those followers changes the role to a forwarder, and then everything that is written to that region will be forwarded by this forwarder to the other region. So they will also like kind of replicating the data behind the scenes. So we will have this kind of globally distributed picture that we had. But with great power comes great responsibility. So we need to now take care of cap theorem. Why do we need to care about that? And what is that? The C stands for consistency. It means that I will always read my latest write, or I will always read the latest write. I mean, I should always read my latest write. And A stands for availability, which means no matter what's going on in the system, I always get a response back when I'm reading something. It might not be the latest write, but I get something back, right? I don't want to not getting anything back. That's availability. And the partition tolerance speaks about if part of the system is not available, how does the system react to this? If the network is down between 2 nodes, if one node goes down, how the system reacts to these kind of situations. And as we know, distributed systems and fallacies of distributed systems, partition tolerance is always, network is always there. If we consider that network is reliable, or I don't know, I don't have any latency with the network, or those things, I'm just fooling myself. And so we always have this partition tolerance there. so we cannot choose it or not choose it. It is enforced. Then we have two options to choose. Either I'm choosing consistency. That means I want to make sure that in this globally distributed system that I have, or in this system that I'm designing, I'm always getting the latest right. So I'm heading for consistency. Or I could go for availability. Nothing blinks. So I could go for this red one, and I say, okay, I sacrifice a little bit of consistency. If it is not the latest right, nothing would go wrong. But I always want that my customers getting the latest, getting some response back, and they are able like to work with the system. And that means that we need to take a look into how consistency levels work in Azure Cosmos DB. So the first one, it has 5 different levels of consistency. The first one is a strong consistency. Is it animating? All of my slides are broken. I don't know why. So it means that I am in region West US 2. I could read everything that I'm writing in West US 2. And I could also, if I'm connecting to East US 2, or I don't know, Australia East, I'm also reading the latest write. So the nodes are representing kind of the writes that are happening in one region. The next level is bounded staleness. It means that there might be a slight delay between getting the latest write. It could be number of versions of a document. So I'm writing a document, I'm updating the document, I'm doing something. So it could be like number of versions of a document, or it could be different documents that I'm, it could be like a time span, like 5 seconds, I don't know, 10 seconds. These are like things that we could configure in our system, what it should be, this delay. So if I'm writing something in West US, I still get the latest write on West US, but in East US and Australia East, I'm having some delay, and that's acceptable in our system, right? So we could go with the bounded staleness. The other one, which is the default consistency level in Azure Cosmos DB, is the session consistency. Unless the other consistency levels, the 2 that we just saw and the two that we will see, this one is a client-side version. The other 2 are handled at the server side. This is at the client side. So whenever I'm writing at West US 2, I'm getting a token back from the Cosmos DB. And when I want to read the data, I could pass this token to the Cosmos DB, and I said, this was my write, right? And if I'm passing that to the East US 2, maybe the data is not replicated yet, but East US 2 will ask others, I got this token, who has the data, give it to me, I need to respond back, right? And then it replicates the data, returns the data back. If I'm still connecting to the West US 2, I'm fine. It doesn't matter, right? If I don't have the token, still I get my latest write. But if I lose the token, if I don't keep the token around, and I'm going to another instance, then it's bounded staleness. We need to wait. It's eventual consistency. We need to see whether the data would be in here or not. You know, we don't know. So if we need like this functionality, we need to make sure that this token exists or kept in our system in further requests that are coming in. Then we have consistent prefix, which is hard to explain, but I'll try my best. So the consistent prefix says if document A and document B are modified in transaction 1, so this is like the first version of these 2 documents. And then I have document A and B again, and in another transaction, so in transaction 2, and they change to version 2, it makes sure that I'm on the other servers or on the other instances, I'm always seeing either version 1 of both of them or version 2 of both of them. The order is not preserved, but it ensures that changes in one transaction are always replicated together. So in the other instance, did I describe it well? Questions in this one? Okay, so if I'm changing something in transaction 1, whether it's one document or n documents, and I'm changing those in another transaction, on the replicated servers, I'm always getting the result of transaction 1, or I'm always getting the result of transaction 2 until everything is replicated and all the instances have the same data, right? So it is guaranteed that the transactions are secure in replication. And then we have eventual consistency, which is our favorite one. There's no guarantee on what is where. And so the system is free to decide when to replicate and when the data is written to the other side, which might be fun, fine and fun. Depends on like your business requirements. Yes. And we are software engineers, so we need to come up with trade-offs. If we want a stronger consistency, it comes with high latency and lower throughputs, and we need to shift the handle to the left side. And if we want weaker consistency but lower latency, the latency here means from the time the request comes to Azure Cosmos DB until we get the data back to the user, kind of thing, and higher throughput. Because if we go eventual consistency, we don't wait for anything to be replicated or getting confirmation from any server, right? We just write on the in the Cosmos DB. Maybe a good scenario for write-heavy systems, right? But if we go for strong consistency, when we are writing something in one instance, this instance needs to send it to all the followers. The forwarder needs to send this to the other regions. And we need to still wait until the other regions confirm that they got the data back. All the forwarders or the followers in every one of them have the data, and then we respond back the data to the user. So that's why we have latency in here if we go for a strong consistency. And the other feature of Azure Cosmos DB that really helped us to improve our system was the change feed data capture. It comes out of the box, and as far as I know, it's free. Don't quote me, but I think it was free. But the Azure functions or the I don't know, application that you host somewhere, it just that one is not free. But consuming this is free, I think. So it gives us the data that is written to Azure Cosmos DB in order. It guarantees that every time I'm getting this data in order. And that is important, for example, when we are designing a system that order matters when we are informing other systems, or we want to consume the events that happened in our system in order, and we cannot like separate those things. And we could use it for different scenarios for creating notification systems, for example. Like we have a system, the customers could register, they could have update their contact info and everything, but maybe we don't want to inform every other systems until someone confirms the registration, right? So we could have this reactively respond to changes that are happening to this stream of events that is going on in our system. We could have data movement. We could use CDC, change feed, to listen to the change feed and move the data as it's happening, either to replicate it to some other things, moving, I don't know, to a data lake. So we could use it for moving data between different kind of systems. And also we could do it for stream processing with different services that are available for us. How it works is that if we write something on the logical database has a logical change feed. It guarantees that everything that is happening is in order, but they are replicated to physical instances. So the change feed for physical instances is also available. And the scalability of the consumers is kind of by default, depends on the number of physical instances that you have, physical partitions that you have. Because we want to guarantee order. We cannot scale systems that both are consuming from the same physical instance, because then you cannot guarantee the order of which application is consuming faster than the other one, right? So this is like the scalability of the change feed in here. You could even create your own implementation. This is for Azure functions, but you could also implement your own version with the SDK. It provides us with a feed iterator or change feed iterator. And in this one, you could even actually say, I'm interested in change feeds of this specific partition. So you could now scale based on the partitions that you have designed, not the physical partitions, but the logical partitions. So you could get those changes in order. And so yes, this was like our system. We just had an API getting the requests, writing all the events in our system, And by the way, one of the things that you could also, one of the other patterns that you could use next to the transactional outbox pattern is listen to yourself. So when a request comes in, instead of saving it to your database, you could just publish an event, right? And also you as the publisher, listen to the event that you published, and then in that process, you just do whatever you need to do. That this is also like another pattern you could leverage when you are designing your system. And then we use the change feed capability to publish it to other systems. And since the system that we have designed, one of those things consuming from the change feed was an application that wants to create read models in our system. So it was like a reactor or projector. You might heard it with both names. And it creates like the projections and read models for our read queries, and we were optimizing it for there. I have some codes as well. I'm not sure how it will work. Let's see. So we have a Cosmos DB in here. I hope it's, do I need to zoom more, Stefan? Fully. Good? Oh, okay. Now? Okay. So I have a Cosmos DB. I cannot see anything in here anymore, but we have an ID, and this stream ID is the partition key that we have designed. So every event in our system has an stream ID, and this is where we put all these events that are happening together. We group them by this stream ID, and then we store them in here. And then we have a snapshot container. So we have another application listening to the change feed of the main one, the customers, and putting the data, creating a read model of that those events and putting it in here. I'm switching here. I think I need to also go to presentation mode. Let's see. Stefan, give me. Yes, sure. That's the purpose of the whole thing. Let's see. Not this, but tell me whether it's fine or not. Is the code fine?
It's a bit more, and when you increase the website a bit, then it's
now? I mean, I could also go. Yeah. Let's see where I am. Okay. By the way, don't store your connection strings on private fields and share it with the whole internet. That's not a good practice. Yes. Use regions for that. Okay. So here I'm creating a Cosmos client from the SDK to connect to the database and the container that I have, and yes, and fetch the data or write the data. And one of the things that you could use is the application preferred regions. This is helpful when you are globally distributed your database, and then you also have your application, web app, whatever it is, deployed to those regions. Then you don't want the application from, I don't know, North US to read from the West Europe, right? So this is where you could also configure like this application now, its preferred Cosmos DB region is North Europe or West Europe or whatever is closer to that. So this is a configuration you put in for your application. And this is one thing I wanted to mention. And the other thing is it is just inserting items or events in our scenario into this container that we have. So as the events, different events coming to our system, like customer registered, order placed, I don't know, order confirmed, order delivered, whatever we have, it just writes that event to the store that we have. And they all, like all the orders of one customer share customer ID, for example, as a stream ID. So all of them are grouped together. If I have a request for customer A, then I know that all of them are like in this partition. I could just fetch them immediately. And this transactional batch is the thing that makes sure if we have like another item written in here, the commented line, then they will both be in the same transaction. That means either both of them will be written in this logical partition or none of them will be written. In my case, I just commented it because we don't have that scenario. So this is the producer side of our application. I have another application. This is the async snapshot. And it is an Azure function which reacts with the Cosmos DB trigger on top of, with Cosmos DB trigger on that, which means it is listening to the change feed of the container that we are mentioning. So we have not a good time for updating. I have a container name in here. I have the database name in here. And then I could also, because this is consuming the change feed, it needs to track how far in the change feed it read the data, right? So it should know like 10 events from the change feed has been consumed by me. And next time that it is running, it needs from the 11th one, right? And it stores those things in the list container that we have in here. And I just said that, yes, you could create the list container if it does not exist. So it is like a configuration. But the list container is basically for keeping track of how far each of these Azure functions or applications. If you're creating your own application, you need to care of that yourself. But Azure functions do that automatically for us. And again, here we just get the event that was written. We deserialize it. We create a customer instance out of that, which is this thing. So we have this customer with customer ID, full name, email, date of birth, everything, and different kind of events like customer created, email updated. And it will create a snapshot and we'll store it in a separate container because we have different read requests and write requests coming to our system, so we could adapt those containers based on our requirement in this system. Just to show a demo, hopefully it's not gonna fail. Let's run this one and going in here. Let's try to. So you see it is trying to write, it is writing some events to the database. And now that I'm running the other application, it is now getting some data from the change feed. And if I'll go here and if I could find a refresh button, you will see that the data in the snapshot are coming and they are like Elnora Torp, and the customers are also now, if I refresh. So as the events are coming, so here it is email updated, the other one is customer created, and these are just our events we are storing, and here we are getting in a snapshot. And I'm gonna stop all of those things because then I need to pay for it. And let's go back to the slides. Cool. So far, so good. So we have some news. We are going to have CodeCrafts conference on May 22nd. And this will be the 4th year, if I'm not mistaken, right? Squaries, yeah, the 4th year. And we have a great lineup this year from Kent Beck, Adam Thornhill, Mark Richards, Neil Ford, Susanne Kaiser, and Abraham Pupko. And yeah, and we also, I think we have 3 more to announce, but let's see. And because everyone spotted the person at the beginning, so here's a discount voucher if you want to buy the tickets. This is the discount voucher. I just give you time to yeah, you're taking screenshots of this, but not scanning my QR code. Yeah, yeah, I see how it works. Yeah, I should have done that. I mean, I also have some discount codes if someone scans the QR code. Okay, everyone took a picture? Could we go next? Okay, good. Then we have also workshops. Workshops from what is trending now for AI with people from Square. Keno and Alfred, 2 of my great colleagues, will present the AI workshop. And if you're also a DDD enthusiast and want to know how to apply strategic and tactical patterns in your applications, then Paul and Martin will hold like a DDD workshop. I highly recommend it. I always learn from them when I'm talking to them. No matter how many times I talk to them, I always learn something new from them. And also we have architecture workshops from 2 known figures in the world. Neil and Mark will hold 2 workshops separately. One is about software architecture fundamentals. The other is about the hard parts of that. So depending on your seniority level and interests, you could choose which one would be benefit. And again, if you want more information, here's a QR code. Let's see. I mean, I should have changed the slides, right? The discount should have been after. Really? No one? Okay. Okay, to summarize what we have discussed in this event, we talked about event-driven architecture. I mean, yeah, we talked about it. But so when you have high volumes of events, when you have a requirement for real-time processing, scalability is a primary concern. So if you don't need to care about the scalability, don't even think about it, because any other architecture would just fit. I mean, hopefully. And requires immediate actions or reactions to whatever is coming to your system, and you need to respond to those things. Two related patterns that might help are CQRS and event sourcing. And again, these two are not married together. So whenever you hear CQRS, do not ask where's your event source. They are separate things. You could just apply them whenever is needed. And Azure Cosmos DB, it was the one that helped us to solve the problem that we had with the scalability of our database and being able to process as many as requests as coming to our system. And then we are making sure that we are responding to everything. If you enjoyed this talk, here is our, we shouldn't use QR codes. No one is gonna scan that. I mean, go to our portal. There's like a link there. You could just check the position, like open positions, and yeah. And again, another one. Follow us on Meetup, and this is your last chance to get awesomeness from my blog and YouTube. And if no one is I need to take a selfie if you don't mind, because I want to remember the faces of people who's not scanning my QR codes. So everyone, please say cheese. Thank you so much for participating. If you have any questions, I'm here. I hope I could answer them. If not, then ask some more experts about it. I'm sure you will find someone. Yes.
Hello, thanks for your talk. We built a quite similar system, just not with Cosmos DB as the main protagonist, but with Azure Service Bus. And our main problem was that the Azure functions were too slow picking up new messages from that service bus. Did you encounter any similar problems using Cosmos DB?
I mean, there are two different concepts, like Azure Service Bus and Azure Cosmos DB are like two different aspects,
Sure.
right? And it has some delays, as I mentioned. Like each of these services has their own scalability when it comes to Azure functions. Like they have different type of scalability based on, for example, for Cosmos DB, it's the physical instances. So to scale that, we just designed our RUs in a way that we have like provisioned physical instances, so we could scale that in that way. And I think we had like 3 physical instances, and we didn't really have that much of delay that is problematic in our scenario. And as I mentioned, if it is problematic, you could use the SDK, but it comes with a difficulty that now you need to group the partitions, like logical partitions for each instance that you're running an application. Then you need to take care of the offset that you have consumed those things. But we have this issue with Azure Event Hubs, and then we need like to do some other magics with the Event Hub to make sure that the Azure functions are scaling depending on things. So what I could recommend is just like take a look into how Azure functions scale out for that specific service, because as far as I remember, they have like different functionalities.
Thank you.
I hope that answered or helped.
From the live stream, Wolfgang did scan your QR code and also said it's a great talk.
Thank you.
The question is, what is your attitude towards the outbox pattern? It seems to be a little controversial in your company.
I mean, every pattern is like to solve a problem, right? If I have a knife, I could cut my hand or I could cut a fruit, right? It's like how we are using that. But I used to use it a lot before, like even before I joined Square. So it was my problem, not the company thing. But as I mentioned, there's also like another pattern in event-driven architecture. You could like listen to yourself, to not using the transactional outbox pattern. And I think David Leitner has also an article on our blog post about like don't overuse transactional outbox pattern. So maybe that could also help like to get some insight about that.
Thanks. We got another question about regarding the dual write problem in the transactional outbox. What if the server could what if the server still crashes inside a unit of work? If one thing is committed but the other one is not, is there a way to mitigate that?
That's the point of transactional outbox pattern. So the unit of work, maybe I should like go back to the code. Here, the unit of work that commits, it wraps both of them inside the transaction. So if the transaction crashes, none of them will be written, right? So the system is still in a consistent state, right? I have not written anything in my system. I have not informed anyone about something, and the other way, right? But if it succeeds, then I have time to inform the people about or other software components about the system, right? So that's the whole point of transactional outbox pattern. And the user actually sees that its write was not successful. So I could even like return a bad request, or I don't know, a 500 or whatever is important, like to return to the user, and the user could retry, for example, to submit an order, for example, in this scenario, right?
This also answers my question about cancellation. We have one final question, or no, not a question, but maybe an initiator for discussion. You mentioned that to have one sender for an event. In Wolfgang's opinion, it could also be that the same event is used or emitted by multiple services. It depends. Do you have some experiences on that you would like to add?
I mean, if by multiple services he means like multiple instances of the same service, yes. But for the other things, I really don't. Maybe because event belongs to something that is happening in one service, right? So if something is happening in this service, I want to inform others about that. And if they are interested, they will do something else. Maybe they have the same name, but the intention of those things might be different because they are into different bounded contexts or into different services. I hope that helps.
And one final comment from Hofrat Karl. So basically, the listen to yourself pattern is basically the read your writes from the 90s. I love how things keep coming back.
Yes, of course. Okay. Any more questions? I'm getting back to. Yes.
So is there any level of control over how you can separate the logical partition into physical partition? Is it always the replication of the schema? The schema is always the same, or you can, for example, have different types of entities separated to different physical partitions? Is there like any level of control you could have over it?
I didn't. By a schema, you mean like the JSON schema?
No, like let's say we have all of the entities are always stored all the same. All type of the entities are always stored in every type of database or logical partition, or can we somehow, like for example, store one type of entity in one logical partition and another type of entity in another? Do we have any level of control of how we separate this data on the base of types?
So here, this is the partition key that we are defining for this container. So it doesn't matter whether they are the same type of entity or they have the same look and feel, like as a JSON document. They should all of them have a stream ID property, right? The level of control is like you could have hierarchical level of control. So you could say I have tenant A, and within tenant A I have a stream ID, right? And then that would be like so each stream ID in every tenant would have 20 gigabytes of thing. So in a hierarchical way, yes, you could control like because you could also go for like every tenant is a separate container, right? You could say I have one container, but I'm going hierarchical partition key, and I have like tenant ID, stream ID as a partition key. This is the level. But what type of documents you're storing in that doesn't matter. You could store everything. As in my example, I stored email updated and customer registered. Both of them are two different type of entities or events in the same logical partition. Another customer was stored in another logical partition, which could or could not be on the same physical instance as well. I hope that answered. Yeah.
Any last questions? Or on stream, any questions?
Do we have pizza?
What? I saw some boxes, but I quickly need 2 minutes.
Oh, okay. So should I unplug the HDMI now?
Yes, please. So quick technical
Here you
change. Let's see.
Yeah, I grab my laptop. Here you are. Stage is yours. Thanks everyone for participating again.
All good on good. Yeah. Thank you. Where are you? No, come here.
I
You're
will.
too fast.
The moment.
You are one of the fastest speakers to get away from the stage ever. So thank you for giving the talk, and as every speaker in our meetups, you get our logo as a custom coaster with our logo. Thank you. Sure. Well, we always look for speakers. Okay. Good. Yeah. Thank you. Yeah. Thank you also to you all here at location for joining and also on stream. Thank you our sponsors, First Square for hosting here, and Rubicon and JetBrains. And yeah, we will quickly do the raffle. So let's see who is the lucky one. We need music for this the next time. So Thomas Pichler, congratulations. Here or on Twitch. Then please contact us at team@.netdevs.at, and we will try to get you your voucher in the next days. And with that, I'm not trying to post to have a QR code. let's see. One is there. Yeah, we always want to improve these meetups, these events, and for that we need your feedback, and would mean a lot to us. QR code for here in the audience, link at the chat for the viewers. And good. And yeah, have a nice rest of the day. See you next month with DataSync Community Toolkit, effortlessly integrating data in modern offline client by Raul and David at TechTalk. And with that, bye. Bye, stream.